Let's call this part 1 of this video. Something you do a lot of in chemistry, it's sums. I definitely wouldn't say mathematics. You tend to think of geometry, algebra, or even trig when mathematics is mentioned. But in chemistry, it's mostly a sound understanding of arithmetic you need, and that is up to first year university level. It's of no use to you working everything out in a calculator because you have to get to understand what's happening when you convert units, scale things up, scale down, use ratio and proportion, percentages, and even work out how much something costs. Well, obviously the chemical industry is composed of commercial, industrial businesses that depend on budgets, knowing how much raw ingredients cost, how long it will take to turn those raw ingredients into products that they can sell, and of course all these things cost money. So calculations in chemistry have a very practical application. Let's kick off this series of videos with something called relative atomic mass. This always seems to stump students. The relative bit is easy to understand. You might have heard the phrase, "It's all relative, isn't it?" Well, someone could say eating greasy French fries will give you a heart attack. It's all relative and related to how many French fries you eat and how often you stuff them into your gob, with other factors like what is the rest of your diet like, how much exercise you take, and the stresses in life you are subjected to. And equally you could say 1,000 is a big number. Well, it is relative to 1 or 5 or even 10. But relative to 1,000,000, it's small. Someone might even say, "You're fat." Well, you might be, but that is based on the ideal proportions of someone who isn't fat, such as a skinny model, or someone with a perfect athletic physique. But relative to someone with 5 bellies and an arse the size of a tractor, then you would probably be thought of as thin. So relative is all about comparisons. And in chemistry, the relative part is you comparing each and every one of the elements from the periodic table with a standard element, and that being carbon-12. A very good element to use as a standard on account of it being absolutely everywhere and in every living thing on the planet. Look at the picture here. 3 elements, atoms. On the left we have helium. On the right we have magnesium, and in the centre, the standard, that's carbon-12. A little bit of arithmetic tells us that carbon weighs 12 atomic mass units. I did outline this in a previous video, what atomic mass is, or what the atomic mass unit is. So just for simplicity itself, let us just say that an atomic mass unit means either a proton or a neutron. So here are the atoms of the same 3 elements again, and thinking about the relative part again. Take helium first. We only use the protons and neutrons when working out how much atoms weigh at this level, because the atoms of different elements are different because of how many of these protons and neutrons they contain. So, we can compare them by just comparing how many protons and neutrons one atom has relative to another, because they'll all contain just protons and neutrons in their nuclei. I think that makes sense. 1 proton equals 1 atomic mass unit, and 1 neutron weighs 1 atomic mass unit. That means we can simplify and state that helium weighs 4 atomic mass units, carbon weighs 12 atomic mass units, and magnesium weighs 24 atomic mass units. So the relative part, relative to carbon, magnesium weighs 24 atomic mass units, and this is because we know carbon weighs 12 AMU. And relative to carbon, helium weighs 4 atomic mass units. Carbon is 3 times heavier than helium, and magnesium weighs twice as much as carbon, but 6 times heavier than helium. It's all relative. So you can see why we don't need to use the actual mass of individual atoms when drawing comparisons for chemistry at this level. That's not to say we don't use awkward numbers in chemistry, of course we do. Now for part 2. We need to take the relative idea a stage further. For this we need to know what an isotope is. So let me explain it. Isotopes are atoms of the same element that weigh different amounts. How can this be? Simple, basic chemistry. Being able to say with certainty that a sample of carbon is pure carbon is because atoms it contains all have 6 protons in their nuclei. Or a lump of sodium metal is in fact sodium because all of its atoms only have 11 protons in their nuclei. That's obvious. Many of the elements that you see on this periodic table have atoms with the same atomic number but different numbers of neutrons in their nuclei. Easy way to explain this is to show you this. The first atom of carbon, and it is carbon, as it's carbon, it has of course 6 protons in the nucleus. It also has 6 neutrons. The one beside it again has 6 protons in its nucleus, but this time it has 7 neutrons. And the other one here has 6 protons, but it has 8 neutrons. So the first one weighs 12 atomic mass units. The second one weighs 13 atomic mass units. And the third one weighs 14 atomic mass units. These 3 carbon atoms are still pure carbon atoms because it's the proton number or atomic number that gives it its identity. These are what are known as isotopes. Atoms of the same element with different mass numbers, that's all. So where does the relative part come in, and what is the difficulty? The difficulty arises in textbooks and other explanations. Not this one, of course, this explanation here on account of me explaining this so beautifully. You have seen a periodic table in a classroom or in a lab whereby the atomic mass numbers have 2, 3 or even 4 decimal places, and that sounds a bit odd. This is where isotopes come in and the standard carbon-12 again. So let me update you with the correct term for relative atomic mass. The carbon-12 isotope is the standard atom against which the masses of other atoms are compared. The relative atomic mass of an element is the average mass of its atoms compared to 1/12 of the mass of a carbon-12 atom. Bit of a mouthful. The relative atomic mass of an element is calculated like this. The mass numbers of its isotopes and the abundance or how many of these isotopes are present. Can we put that into some plain English? So, relative to this carbon-12 isotope, if we had an isotope of magnesium which is 24 atomic mass units or 12 protons and 12 neutrons, 24 subatomic particles, magnesium is exactly twice the mass of carbon. So yeah, that's a bit easy. The relative bit means that you can't just say in general terms that a magnesium atom is twice the mass of a carbon atom. Why? Because in nature, in real life, magnesium has isotopes, in fact 3 common isotopes, magnesium-24, magnesium-25 and magnesium-26. And here they are. Have a look at the pictures and you can count up the protons and neutrons if you like. Because of this, and science being science, we need to be a bit accurate in the things we add data to. So on the big complicated periodic table you see on laboratory walls where the mass numbers are not integers or whole numbers, it's because when calculating the mass number of, let's say, magnesium, we need to take account of these 3 different isotopes of magnesium. Some quick arithmetic. Let's say you can, a bit difficult, but bear with me. Let's just say we can find a small random sample of 100 magnesium atoms in nature. They're just kicking about the room somewhere. We can pick them up. And let's say out of this 100 magnesium isotopes, 9 have a mass number of 25 atomic mass units, 8 have a mass number of 26 atomic mass units, and 83 have a mass of 24 atomic mass units. Then we can take an average like this. Have a look at the sum. And let's do the calculation. This gives us an average of 24.250 atomic mass units, and of course you can't have 0.250 of an atomic mass unit. Of course you can, but that doesn't matter. This is relative atomic mass that compares the mass of carbon with the average of the mass of the element and its isotopes. Do hope this makes sense. Contact me if you're in any doubt. All for now.